In the early 1960s, the United States made an audacious attempt to build the world's largest radio antenna by launching nearly 500 million copper needles into orbit. In a nuclear war, it risked losing the ability to communicate with its own forces. The solution was to turn orbit itself into infrastructure. Deeply controversial from day one, Project Westford sparked outrage among the international scientific community. It worked, briefly. It also left behind consequences nobody fully anticipated. Throughout the late 1950s, military planners in Washington were haunted by a nightmarish scenario. Not the threat of a Soviet nuclear strike. That was terrifying enough already. But what could potentially happen in the immediate aftermath? The order to retaliate would be rushed out to bases in Europe, fleets in the Pacific, and submarines lurking beneath the Atlantic. But nothing would come through. The line would be dead. The signal gone. The most powerful military on Earth would be unable to speak to itself, and the American people would be left helpless. This was no paranoid fantasy. It was a genuine operational vulnerability, and the infrastructure underpinning long-range communication at the time did almost nothing to conceal it. Two systems kept America connected to its overseas forces. The first was a network of submarine cables running across the ocean floor, physical objects in fixed locations whose coordinates appeared on maps that the Soviets also possessed. TAT-1, inaugurated in 1956, ran from Scotland to Newfoundland and could carry just 35 simultaneous telephone calls. A single hostile vessel with the right equipment could sever it in an afternoon. The second was the ionosphere, a shell of electrically charged particles encircling the Earth at altitudes of between roughly 30 and 600 miles, off which radio waves could be bounced across vast distances without any physical infrastructure at all. In theory, a reliable fallback. In practice, anything but. Solar storms could knock it out for hours or days at a stretch, with no warning and no remedy. Cut the cables, wait for a solar storm, or both, and the United States military, in the most critical moments imaginable, would be effectively deaf and mute. The question of how to fix that was one of the defining problems Washington faced in the early Cold War. The answer, when it came, would be like nothing anyone had seriously attempted before. MIT's Lincoln Laboratory occupied a research station on Hanscom Air Force Base, northwest of Boston, a Department of Defense-funded facility where some of the country's brightest scientific minds were quietly working on problems the military didn't advertise. It was there, in 1958, that an engineer named Walter Morrow proposed something that sounded, on first hearing, closer to science fiction than military strategy. If the ionosphere was unreliable, they could simply build a better one, a permanent one. A ring of copper wire placed in orbit around the Earth that would reflect radio signals across any distance, in any weather, and any hour, regardless of what the sun was doing. Each wire would be around 3/4 of an inch long, precisely half the wavelength of the 8 gigahertz signal that would be beamed up from the ground. At that length, each filament would behave as what engineers call a dipole antenna, capturing the incoming signal and re-radiating it in all directions. Multiply that effect across 480 million individual wires, arranged in a belt circling the globe at around 2,200 miles up, and the result would be the largest radio antenna ever constructed, not by any single nation, but by physics itself. The endeavor was initially called Project Needles, but it would later be renamed Project Westford, after the neighboring Massachusetts town of Westford. It was an audacious idea, but it was not an isolated one. The early space age was thick with schemes of comparable ambition. Science fiction author Arthur C. Clarke had suggested as far back as 1945 that repurposed German V-2 rockets could deploy antennas into geostationary orbit. The U.S. Navy had bounced radio signals off the moon in 1946. NASA was developing Project Echo, a pair of enormous metallic balloons that would serve as passive microwave reflectors in orbit. In that context, a belt of copper wire seemed almost modest. And space, after all, was vast. The risk of anything going wrong up there, of anything colliding with anything else, seemed almost too small to worry about. Almost. The astronomy community noticed Project West Forward almost as soon as it became public, and it did not like what it saw. Radio astronomers were the first to raise the alarm. A belt of copper wire encircling the Earth at 2,200 miles would sit squarely in the path of signals they had depended on to study the universe. Optical astronomers followed with concerns of their own. A dense permanent ring, they argued, could scar the night sky in ways that ground-based observation might never fully recover from. The Royal Astronomical Society lodged a formal protest. But underneath the scientific objections ran something more personal. Project West Forward was a military program, and it had been planned, funded, and advanced without any obligation to consult the scientific community whose work it would directly affect. Astronomers weren't asked. They were simply informed, after the fact, that 500 million copper wires were going into orbit above their telescopes. British radio astronomer Sir Bernard Lovell put it plainly, quote, "The damage lies not with this experiment alone, but with the attitude of mind which makes it possible without international agreements and safeguards." Fellow British astronomer Fred Hoyle was less diplomatic still, accusing the United States of conducting a military project behind a facade of respectability. In his view, it was an intellectual crime, committed not just against science, but against the principle that space belongs to everyone. The pressure was sufficient to draw the White House into the debate. President Kennedy moved to broker a compromise. The experimental dipole belt would be placed in a relatively low orbit. The wires would be designed to re-enter the atmosphere within a few years, and no further tests would be conducted until the results of the first had been fully assessed. The Space Science Board of the National Academy of Sciences convened a series of classified discussions. Ambassador Adlai Stevenson was dispatched to the United Nations to reassure member states that the United States was acting responsibly. Most remained unconvinced. The assurances were noted, the objections recorded, and the launch preparations continued regardless. By fall 1961, the rocket was ready. The world was watching, skeptical, frustrated, and in some quarters, quietly furious. On October 21st, 1961, an Atlas Agena rocket lifted off from Vandenberg Air Force Base in California and delivered its payload to the intended orbit. The hardware had performed exactly as designed, but the needles had not. The dispenser mechanism responsible for releasing the copper wires had failed to spin up. Without that rotation, the needles simply stayed put. They'd been packed into their canister in blocks of naphthalene gel, a substance not unlike the active ingredient in mothballs, which was designed to evaporate in the vacuum of space and release the wires into a thin, dispersed cloud. None of that happened. The wires stayed where they were, going nowhere. Whether they remained in their initial configuration or eventually broke apart into untracked fragments was never fully determined. The first attempt at building an artificial ionosphere had produced, as far as anyone could tell, nothing at all. Perhaps unsurprisingly, the Soviet state newspaper Pravda was not sympathetic. Seizing the propaganda opportunity to paint their rivals as irresponsible polluters, it ran the headline, quote, "USA Dirty Space." It was a charge that carried a particular sting, given that the launch it was condemning had failed to put anything in orbit in the first place. Ambassador Stevenson, who had spent months reassuring the UN that the project was being conducted responsibly, now found himself back before the international community, defending an experiment that it achieved nothing except renewed suspicion. He pledged closer consultation with the global scientific community before any second attempt was made. The pledge was noted, but the skepticism did not dissipate. Back at Lincoln Laboratory, the engineers set about diagnosing what had gone wrong and redesigning the dispenser mechanism. The project was bruised, but it was not finished. 18 months later, they would try again. On May 9, 1963, a second Atlas Agena rocket lifted off from Vandenberg. This time, everything worked. The redesigned dispenser released its cargo cleanly into an orbit approximately 2,300 miles above the Earth, tracing a path that crossed both poles. Over the following 6 weeks, the needles gradually spread along their orbital track, thinning from a dense, concentrated mass into something altogether more extraordinary. A ring encircling the entire planet, roughly 9 miles wide and 19 miles thick, composed of 400 million individual copper filaments, each one about 3/4 of an inch long and thinner than a human hair. For a brief moment in the summer of 1963, Earth had rings. Not like Saturn's, nothing visible from the ground, nothing that would have been apparent to anyone looking up, but a ring nonetheless, quietly orbiting above every continent, every ocean, every city on Earth. The first communications test came 5 days after launch, on May 14th. Engineers transmitted voice signals across the continental United States via the orbiting copper belt, using a pair of dish antennas 60 feet across. One at Millstone Hill in Massachusetts, one at Camp Parks in California. The connection was described as intelligible. Data moved at around 20,000 bits per second, roughly the speed of an early 1990s telephone modem. By the standards of 1963, it was a landmark achievement. The experiment had proven that a passive orbiting reflector could carry real communications across real distances. But the window was narrow. As the needles continued to disperse, spacing further and further apart, the signal degraded. By June, data rates had fallen to around 400 bits per second, barely functional. On July 2nd, the experiment was formally concluded. The ring that had taken years to plan, 2 launches to achieve, and 6 weeks to form, had lasted as a practical communications tool less than 2 months. The engineers declared it a technical success, and in the strictest sense they were right. But even as they were writing up their results, the ground was shifting beneath them. The year before Westford's successful launch, something had gone quietly but decisively wrong for the project. Not in any laboratory or launch facility, but in the broader landscape of what space technology was becoming. On July 10, 1962, AT&T's Telstar 1 satellite had lifted off from Cape Canaveral, and within hours, beamed live television pictures across the Atlantic. It was compact, it was capable, and it carried its own power source and its own transponder, an active system that amplified the signals it received, rather than merely bouncing them onward. Compared to Westford's passive dipole belt, which required enormous 60-foot ground antennas, and delivered, at best, the communications equivalent of a dial-up modem, Telstar represented a different order of capability entirely. Westford was a dinosaur before it had fully evolved. No more needles were launched after 1963. The controversy did leave one concrete mark. The 1967 Outer Space Treaty included a provision requiring nations to consult internationally before undertaking experiments that might interfere with the space activities of others. A direct consequence of the Westford debate, a small but durable monument to the argument the astronomers had made. As for the needles themselves, most were expected to re-enter the atmosphere within a few years, nudged earthward by solar radiation pressure. By the late 1960s, it was assumed they were largely gone, That assumption turned out to be wrong. There was a flaw in the design that nobody had fully anticipated. The copper needles had been packed into their dispensers in blocks of naphthalene gel, which was supposed to evaporate the moment it hit the vacuum of space, releasing the wires individually into a thin, dispersed cloud. What the engineers hadn't accounted for was what happens to metal in a vacuum before that evaporation was complete. In the absence of an atmosphere, copper touching copper doesn't just sit there. It welds. The needles were fusing together before they ever had a chance to separate. The result was clumps. Tangled masses of fused copper wire, far heavier and denser than any individual needle. And that distinction matters enormously. A single copper filament, 3/4 of an inch long, weighing 40 micrograms, poses almost no threat to anything it might encounter in orbit. A clump of hundreds of them, welded into a solid mass, is an entirely different proposition. Objects in orbit at 2,300 miles altitude travel at thousands of miles per hour. At those velocities, even a small mass carries devastating kinetic energy. These were not harmless wisps of metal drifting peacefully through space. They were projectiles. The scale of the problem was worse than it first appeared. Only 25 to 45% of the planned 480 million dipoles from the 1963 launch are believed to have dispersed correctly. The rest likely remained in clumps of varying sizes, many too small to track with the radar systems at the time. And then there was the 1961 payload, the launch that had never deployed at all. That entire canister of needles went into orbit intact, and its ultimate fate was never fully determined. The European Space Agency, in a 2001 analysis of the Westford debris, concluded that thousands of additional clumps could have originated from that first mission, many of them potentially too small to detect even today. The International Academy of Astronautics would later call Project Westford the worst deliberate release of space debris in history. Looking at what was left behind, it's difficult to argue with that assessment. As of 2023, nobody knows exactly how many clumps are up there. 44 have been formally tracked, but the 1961 payload alone could have produced thousands more, many of them too small to detect with current technology. They are not drifting harmlessly. They are traveling at orbital velocities in a region of space that's becoming increasingly crowded. And unlike the individual needles, which were designed to decay within a few years, some of these clumps could remain in orbit for decades to come. The astronomers who protested Project Westford in the early 1960s were worried about a relatively modest amount of copper wire. What they were really arguing about, without quite having the language for it yet, was something much larger. The idea that orbit is a shared resource, finite and fragile. Filling it with debris, no matter how temporary or well-intentioned, carries consequences that extend far beyond the original experiment. That argument lost in 1963, and in the decades since, the behavior it was arguing against has continued on a scale that would have been unimaginable to the astronomers making the case. By 1978, NASA scientist Donald Kessler could see where it was heading. His theory, known as Kessler syndrome, was straightforward and alarming. Once the density of objects in low Earth orbit reached a critical threshold, collisions would begin generating debris faster than it could naturally decay, triggering further collisions in a self-sustaining cascade that could render entire orbital shells unusable for generations. It was precisely the concern that Westford's critics had raised 15 years earlier. Not about copper needles specifically, but about the principle that what goes into orbit doesn't always come back down on schedule, and that the consequences can multiply. By 2009, Kessler was warning that the environment had already passed the point of stability. Today, more than 23,000 trackable pieces of debris circle the Earth, with an estimated 600,000 more too small to detect, but large enough to destroy a satellite on impact. On average, one satellite is lost to collision every year. The cascade the astronomers feared in 1963 has not yet fully begun, but the conditions for it are already in place. What's made that all the more consequential is the sheer scale of what now depends on those orbits remaining usable. GPS signals synchronize global financial transactions. Satellite communications underpin battlefield operations. Navigation systems guide commercial shipping across every ocean. All of it circles overhead, dependent on hardware operating in an environment where debris is multiplying. Anti-satellite weapons are being tested, and the rules governing what nations can and cannot do are increasingly difficult to enforce. The original threat Westford was designed to solve, the vulnerability of the systems the world depends on to stay connected, has not gone away. It's just moved from the ocean floor to the sky. Westford was a strange collision of two groups of people who turned out, in retrospect, to both be right. The military planners who conceived it had correctly identified a genuine vulnerability, one that's only grown more acute as the world has built more of its critical systems into space. The astronomers who opposed it had correctly identified that orbit is not an infinite resource, and that treating it as one would eventually produce consequences nobody could fully control. Both arguments were sound. Neither was fully acted on. The project was cancelled. The consultation provision was written into the Outer Space Treaty, and the world congratulated itself on having drawn a line. But the line was drawn around Westford specifically, not around the behavior that had produced it. The launches continued. The debris accumulated. The tensions between military ambition, commercial interest, and scientific freedom in orbit, tensions that surfaced publicly for the first time over a few dozen kilograms of copper wire in 1963, have never really been resolved. They've simply grown larger and more complicated, and the consequences of getting them wrong have grown larger with them. There's a telescope in Massachusetts, built by Lincoln Laboratory, around the same time as the Westford program itself, that has spent decades scanning the sky for what was left behind. It was named Haystack. This name was not a coincidence. It was built, quite literally, to look for needles in space. It is still looking. The needles are still there. And the questions Westford first forced the world to confront, about who bears the consequences of what gets put into orbit, about where military ambition ends and shared responsibility begins, are still, in any meaningful sense, unanswered.